GERDA, the search for neutrinoless double beta decay. Today, we believe that the known universe began with the Big Bang. An equal number of matter and antimatter should have been produced, but there's almost no antimatter left in the visible universe. The reason might be that neutrinos have a special property. They might be matter and antimatter at the same time. Theories predict that unstable heavy neutrinos could have been produced during the Big Bang. Subsequently, they decayed into matter or antimatter with a slight preference for matter. As time evolved and the matter and antimatter particles annihilated each other, a tiny excess of matter remained. The most numerous of the remaining matter particles by far were stable neutrinos. The remaining matter was the seed for galaxies and other large-scale structures visible today in our universe. Although neutrinos are very light, they're the most abundant form of matter particle in the universe. Calculations of the gravitational formation of the structures confirm that the resulting large-scale structure depends on the lightness of neutrinos. Their predictions are consistent with observations only if neutrinos are assumed to be very light, at least 5,000 times lighter than electrons. From other experiments, we know that neutrinos must have mass, but in fact it's so small that so far it's been impossible to measure it directly. The special property of neutrinos, that they're both particle and antiparticle at the same time, could explain why neutrinos are so light. The GERDA experiment is looking for an extremely rare nuclear decay that, if observed, could shed light onto the questions of the matter-antimatter imbalance in the universe and the lightness of the neutrino mass. The decay is so rare that the extremely sensitive radiation detectors looking for it have to be protected against all natural radiation. Cosmic radiation is bombarding Earth constantly. This is why the GERDA experiment is located in the Gran Sasso National Underground Laboratory in Italy, in one of its 3 experimental underground halls, covered by 1,400 meters of rock. A clean room at the top of the GERDA experimental structure is needed to protect the detectors against dirt containing natural radioactivity during the installation procedure into the experiment. When the few cosmic particles that still reach the laboratory traverse the water tank, they emit light that can be detected, thereby allowing identification of this background. This is important as such particles could fake double beta decay in our detectors. Purified water shields the inner parts of the experiment from natural radiation present in the lab. The inner volume of the experiment is defined by a tank filled with liquid argon. The -185 degrees Celsius cold liquid shields the germanium detectors at the center of the tank from the very small amount of radiation emitted from the vessel walls. The location of the detectors is designed to be one of the most radiation-free spots on Earth. The detectors are made out of germanium that may decay by neutrinoless double beta decay. The detector itself detects its own decay, which is, however, so rare that less than 1 decay per detector per year is expected. Neutrino-accompanied double beta decay is a standard process. 2 neutrons, here red, of the nucleus decay at the same time into 2 protons, here white. 2 electrons and 2 neutrinos are released. The neutrinos are so elusive that they escape the experiment without being detected. If neutrinos are their own antiparticles, they could cancel each other out in the decay. 2 neutrons decay at the same time into 2 protons. Only the electrons are released. The full energy released in the decay is absorbed by the detector as there are no neutrinos escaping. Thus, the signal is expected at a very well-defined energy. Neutrinoless double beta decay could reveal a fundamental property of the neutrino. That is, if it's its own antiparticle, and thereby have profound implications for our understanding of the creation of matter and its structures.